Okay, so to get started, as I said in the announcement, since we had two special times for the two Monday lectures in the past 2 weeks, I want to give this chance to everyone to ask any questions you might have about previous lectures and also the homework one, which will be due this week. And I know that some of you might have come from very diverse backgrounds, so that's why we are not assuming that everyone has the same starting level, but I want to ask whether you find anything particularly confusing or difficult to understand from the past lectures. In particular, today's lecture will be a little bit theoretical because we are going to talk about the generalized linear model theory. So the general form of generalized linear model, where we started from logistic regression in our last lecture as the specific example. So now we're going more general today, try to give a general form about how do we fit a generalized linear model, including logistic regression. And later we'll talk about Poisson regression as another specific case example. Okay, so any questions before we get started? I know that this class, the way we introduce the linear model, sorry, I think I need to change the directions I can see the screen. The way we introduce the linear model uses linear algebra because we use the matrix form. So therefore, I think some familiarity with linear algebra is basically required. If that's not something you are expecting, then probably there are two ways. One is to try to make up linear algebra background and then watch the lectures again, or maybe you can defer the learning of linear model in the matrix form later after you became comfortable or familiar with linear algebra. That will be my advice. I know in some applied regression classes, for example, I think in some classes taught in the epidemiology department, maybe they don't use the matrix form. Maybe they just talk about like the R package or the what's that stata package, how to do the programming. But this one, just to clarify, this class is intended to be designed for the graduate students in the statistics department. So that's why we assume the matrix form. But if you understand it, I think it makes things simpler, right, than the scalar form. You don't have to spell out so many terms, but it requires some background. So my strong suggestion for linear algebra background would be the MIT open course for linear algebra. It was taught by a very senior professor called Gilbert Strang, and he has written a very good book about this. So I think that is the best linear algebra course I've encountered myself. So I strongly recommend that for, yeah. Okay, since I don't see questions here, and also as an announcement, I plan to use the after class time as my office hour when needed. And if that's not the time you can make it, you can schedule appointments with me for other times. Okay. All right, so something I want to first start talking about. Okay, let me see. Yeah, this is something which I found very interesting, but I didn't emphasize. I think I might not have emphasized well enough when we talk about linear model is this. So just as a very quick review for linear model, we talk in the first few classes. Try to make this bigger. Okay. So for linear model, we have this residuals, if you recall. We have the EI defined as YI minus YI hat, right? And just as a review, we have the vector Y hat, which is just we stack Y1 hat to YN hat as a column vector. This has the specific form as what? As X beta hat, right? And the beta hat is from the least squares, or it can be from the maximum likelihood estimation. Beta hat has the form X transpose X inverse X transpose Y. And we denote this matrix as the hat matrix. We call this HY. So that's what we have. So therefore, in the vector form, the residual vector E is equal to Y minus Y hat, which becomes identity matrix, which is n by n, minus H times Y. So that's what we gave in a past lecture. And then we said, if we believe in this homoscedasticity assumption, which is, if we write a model, right? The model is, let me just scroll up. The model is yi equals xi transpose beta plus epsilon I. So I'm writing out the model for one observation. Then the heteroscedasticity assumption is that epsilon i's are IID normal with mean 0 common variance sigma squared. So the key here is that the sigma squared is not specific to I, it's common. Otherwise, if it becomes sigma I squared, we call this heteroscedastic because it's specific to observation I. So for this common sigma square scenario, the homoscedasticity. Under this assumption, how do we estimate it, right? We only have an estimate for beta as of now. How about sigma squared? So recall that if we do the maximum likelihood estimation under this normal assumption, then sigma square hat MLE, we can show that it's actually what? It's actually the residual sum of squares divided by n. So I can write it as 1 over m sum of ei squared. Or I can write in the matrix form 1 over m e transpose e. So they are equivalent. And then what's next? Is this estimator a biased estimator or unbiased estimator for sigma squared? The unbiasedness is very important for statistical parameter estimation. So maybe I can ask you this question from your perspective. Why do we need an estimator to be unbiased? What does it mean in reality? Why is it good or important? Have you ever thought about this question? Because we talk about unbiasedness a lot, right? We talk about bias a lot. Why is it important? Yeah. You said large sample?
No, I mean, the estimate of the number, then by taking large number of samples, you can actually get the actual
value. Oh, that's a very good answer. But your answer is about another definition or concept called consistency. It's not a bias. Consistency is about whether your estimator's value would approach the true parameter value as your sample size goes to infinity. That's the consistency concept. So you just state it. Basically, if your sample covers the whole population, you get a true value, right? That's a desirable property. But why do we care about bias or unbiasedness? Any other thoughts? So the definition of bias is this. When we compare the expectation of this estimator, we compare it to the true value. Compare these two values. Maybe you can step back and think about what does expectation mean? What does expectation mean? Average value of the estimator. That's what you said, right? An average of what? Other samples, right? Yeah, so basically it's that I consider the average value of my estimator if I have many samples from the same population. And from each sample, I get one parameter estimate value. Then I calculate the average across these values, whether the average is actually the true parameter value. But why is that a good property? Yes.
Is it for like central limit narrow type stuff, right? So that in the limit, like you want the asymptotic distribution estimator to be centered at the true parameter value.
Mm-hmm. That's a very good point. And I think it's close to what we mean. Yeah. Even though when we talk about bias, it's not necessarily under the asymptotic scenario, right? Because when we talk about asymptotics, it has to be when the sample size is large. But even for small sample size, maybe the asymptotic distribution, like central limit theorem, doesn't hold that well. However, we still want that for this small n, small sample size, the estimator is unbiased. So we hope that this unbiasedness is not related to sample size. It's not depending on the sample size. But the symmetry answer, I think that's the reason. Basically, we hope that by having repeated sample collection. So if we repeat our experiments, then hopefully by averaging our estimates, we are getting closer to the truth, right? But if the parameter estimate is biased, it means that repeat experiments or repeated sample collection wouldn't help. It will be biased towards one way or the other. So you will never recover the true value. So I think that's my understanding of why unbiasedness is important. You hope that even though one parameter estimate value may be off, like on the left or right of the true value, but from other samples, then you can get other parameter estimate values, then together, their collective center mean is the true value. Okay, so based on that, then what's the expectation of this? Actually, we can show that it's actually biased. So here, the expectation, we can calculate it and we can find that it's actually m minus p over m. So we will have this term multiplying sigma squared. And you can see that asymptotically, when you let n go to infinity, the bias is not there because asymptotically expectation is just sigma squared. But when n is not so big, especially when n and p are comparable on the same order, then you see that this term is not 1, it's not close to 1. So therefore, this bias needs to be corrected. And just like when we have the unbiased estimator for variance using a sample, we divide by n minus 1 instead of n to achieve unbiasedness. The same thing here. So here the unbiased estimator for sigma squared. Estimator of sigma squared is actually 1 over n minus p, E transpose E. So we divide by n minus p instead of n. And p is the number of parameters in your beta. So it's the dimension of beta, including the intercept and the slopes of p minus 1 predictors. Okay, how do we derive this? So this is something to get this result. How do we get this result? We will use the matrix form here to help us. So the matrix form will make the expectation calculation much simpler. Okay, recall that we have E as this I minus H times Y. Then we can see that if you have the sigma squared MLE, so maybe I will calculate this. So let's calculate the expectation of n times sigma squared hat MLE. So then I don't need to worry about this 1 over n anymore. Then it's just expectation of E transpose E. Okay. And then the hat matrix will really help us because we actually have this I minus H, but its transpose is itself. And also we have this interesting result. So let me just put in this formula for E. So I get Y transpose I minus H transpose, which is itself, times I minus H times Y. And I can show that this is called the idempotency. So the I minus H times itself remains I minus H. So therefore, this is just expectation of Y transpose I minus H Y. I just need to do this calculation. Okay. And what else? So basically, for this one, we can say that essentially, because we are only getting the EI squared, right? So, and what is the dimension of this one? Let me ask you. It's a good thing to notice. What is Y transpose? 1 by n, right? Y is n by 1. So it's a scalar, right? It's a scalar. Then the good thing is that you can add trace to it. So basically, as a scalar, the trace is the value. So when we add a trace to it, we make the things even simpler for us. The reason is that, you know, by this circular rule of the trace, you can put this this Y in the end to the front, and the trace stays the same. So basically, I'm moving the trace inside the expectation. I'm basically swapping the two. But then you will actually have it as this expectation of Y transpose I minus H. Okay, and now this is no longer a scalar, but this is an n by n matrix. Okay, but what can we do out of this is that for this expectation of Y times Y transpose, this is the only random part. And this is the fixed part, because we assume the X design matrix to be fixed. So the hat matrix, which only depends on X, is also fixed. H is considered fixed. So therefore, when I talk about expectation, I only keep the random part in expectation. And this will give me the trace of this expectation of Y transpose and n by n matrix times I minus H. Okay, so this I minus H is out of expectation, but inside the trace. And then what the remaining thing for me is to get this expectation of Y transpose. And for this, we actually will use this famous variance formula, which is just in the scalar form. I'm just writing it for your review. The fact is that if we want to talk about the variance of a random variable X, right? So it's equal to the expectation of X squared minus the square of the expectation. So that's the formula we will use for the covariance thing. So similarly, here we will say that for the covariance matrix of this Y vector, which is n by 1, this will be an n by n covariance matrix. This can be written as the expectation of Y times Y transpose minus the expectation of Y times expectation of Y transpose. So in the matrix form, I have the same thing. So each term here is n by n. This is like n by 1. This is 1 by n. Okay, and for the left-hand side, the covariance of Y, I already know that it's just sigma squared times an n-dimensional identity matrix, because Y1 to Yn are independent. And this sigma squared is from that error term, epsilon I. And this is what I want. And this one, I know expectation of Y is just X beta based on my model. And this is X beta transpose. So together, you will see that by arranging the terms, right? I can move this term, the second term minus X beta times X beta transpose to the left-hand side. Then I will get expectation of Y transpose just as this sigma square identity minus plus, because this minus becomes plus. I open this up and I would actually get X beta times beta transpose X transpose. That's my expectation for this. And then I will put this inside this term. So expectation of Y transpose times I minus H is what? And by the way, this I is also IN. It's n-dimensional identity matrix. So I put this inside, and you can see that I would just open up the terms. And for the first term, I would get sigma squared I minus H. Okay. For the second term, I would have X beta transpose X transpose I minus H. Okay, and for this term, the interesting thing is that it's actually 0. The reason is because for the second term over here, it's equal to X beta transpose X transpose I is the first term, so I don't need to keep the I. But for the H, let me expand it. X beta transpose X transpose. Recall what's H? H is X times X transpose X inverse X transpose. So therefore, you see that I can have this term, these two terms canceled. Then I'm left with X beta transpose X transpose. So the two terms becomes identical. So then it's 0. So therefore, for this term, we found that it's just equal to sigma squared I minus H. Now I put it back to the trace, okay? So right here, I have derived that inside the trace, it's the trace of sigma squared I minus H. Okay, then I just need the diagonal terms. And I previously showed that we previously showed in a lecture that trace of H, also using that circular rule, we can show that's equal to P, the number of parameters in beta. Then together, this will give me just sigma squared and minus P. So that's how we can derive the expectation of n times the MLE, sigma square MLE, to be equal to sigma square n by P and minus P. So that's how we show the bias. So essentially, I'm trying to say that the matrix form here helped a lot because the cancellations here will be much easier. And I cannot imagine how challenging the algebra would be if you use the scalar form. Yeah. All right. Just think about the matrix as a tool, as a useful tool for our calculation. And by the way, so I just want to make up this piece by saying that, okay, here the n minus p as the effective degrees of freedom of our residuals is because of all these calculations. In particular, we lose this degrees of freedom from the H matrix, and the essence of the H matrix is because here we are basically trying to link our n observations together using the design matrix. So we're not keeping them independently, but they're tied together in this way so that we borrow information across observations when we do the prediction of y hat. So just to have the high level understanding that when we predict the yi hat for each I, we are also using other observations. It's not just based on observation I alone. Okay. So that's something I want to just make up for the linear model part. Now today we will continue with our discussion about the generalized linear model, GLM theory. So in the general form of GLM, generalized linear model. So generalized means that we want to go beyond Gaussian. All right. So when we say from linear model to generalized linear model, what we change is in the two layers of our model. Recall that we use this random structure and systematic structure to describe a model. So in the linear model, the random structure is that each response, yi, is independently following its own Gaussian distribution with mean mu I and common variance sigma squared. So here we are still assuming the simplest homoscedastic assumption. And in the systematic structure, we try to link the mean mu I to our predictors. So we have mu I equals to xi transpose beta. That's the systematic structure. So in the systematic structure, there's no randomness. It's just this relationship, which we assume as a functional relationship, but it's nothing random. The random part, why yi is not exactly equal to mu I, is because of the random structure. And we assume the randomness to be Gaussian. In the generalized linear model, we first want to generalize the random structure so that the yi would be still independent. Sorry, not IID, IND, I should be clear. IND, because the means are different. Independently following their own Gaussian distribution with their own means. So in the generalized linear model, we assume that yi are still independent, but they may follow other distribution. I would just denote that in general as some F distribution with mean mu I. And then the mean mu I may not be real valued. They could have some specific range. Maybe I will just talk about logistic regression. In the logistic regression case, our yi would be independently Bernoulli with mean mu I, right? 0, 1. Then in this case, the mu1 will have the range as 0 to 1. So it's not real value. Then in this case, it does not make sense to assume mu I is a linear combination of the predictors. So here we assume the predictors are, and I should say the predictors multiplied by the weights in the beta. Together, they take real value. So there's no limitation on their range. So in this case, the range of mu I for the Bernoulli would not match the range of xi transpose beta. So therefore, we will need some transformation of mu I, some monotone transformation of mu I, so that this will become real value. So we call this G of mu I is xi transpose beta. And we give this G function a name. So it's called link function, which is a key concept in generalized linear model. So specifically, link function links the mean parameter of each observation of each yi to the predictors as a linear. So basically G mu I after transformation, then it's a linear function of the predictors. So in many cases, we further give this G mu I a notation. We can call this eta I, okay? So you just give G mu I a notation for simplicity, and this eta I is called linear predictor. So you will also see this term a lot in the generalized linear model framework. Okay, so last time we talked about logistic regression. For logistic regression, G of mu I is the logistic function. So it's basically log mu I over 1 minus mu I. And this function is called logit. We define this to be the logit function of mu I. And it maps mu I from 0 to 1 to negative infinity and positive infinity. So 0 mu I becomes negative infinity, 1 mu I becomes positive infinity. Okay, but why is it this function, not other functions? There are other functions that can map 0 to 1 to real values. Why do we choose logit? So today we'll give you the justification from the generalized linear model theory. Okay, so that's what we covered last time. Today, we will give you some general forms of the F distribution and also what's the corresponding G, the link function. So for F, for the random structure, let's just say this. First, for the F, in statistics or mathematical statistics in particular, people like to talk about this exponential family. So exponential family is a general class of parametric distributions. And the distributions we are familiar with, like Gaussian distribution, Poisson distribution, and something else like Bernoulli distribution, binomial distribution, they all belong, and also exponential distribution, gamma distribution, they all belong to exponential family. So this is a generalization. And if we can derive something about exponential family, then it will be directly applicable to all these specific distributions. So in exponential family, we have two parameters. Basically, two parameters. One is related to the location. One is related to the scale. And you can consider them to be generalized from the Gaussian distribution. The Gaussian mean is a location parameter where the center is. And the Gaussian standard deviation or variance, it's a square, is the scale parameter. It indicates the spreadness of the distribution. So similar idea is generalized here. So we write the density function for exponential family. Density function, or it's the probability mass function, depending on whether the distribution is discrete. As I said, Poisson is discrete, but it also belongs to exponential family. Gaussian is continuous, but it also belongs to exponential family. So we just write a general form as the density F of the observed value of our yi. So yi is the random variable, our response. We just use its observed value. We call that small yi. And the two parameters, we denote the location to be theta, the scale to be phi, the two parameters. So in the form of GLM, we care about the mean parameter to be I specific to observation I. So the mean is linked to the location parameter. Therefore, we call theta as theta I. It's specific to observation I. And the scale parameter, just as the sigma square for Gaussian, we assume it to be common for all observations, just for simplicity. And this exponential family takes this form. It's by the name exponential. It is an exponential function for the density. And inside exponential function, there are two terms. The first term is a ratio. So it's yi theta I minus some b function. B is a function applied to theta I. And in the denominator, it's a function of phi. And we assume it here, the AI is a function specific to I. AI is a function applied to phi. So this is the term of our most interest. And a normalization term. This is just to make sure the density function integrates to 1. C of yi phi. So the key thing about the exponential family is that this normalization constant does not involve theta I. That's a very important part of this definition. So you may find this definition a little bit abstract, but basically it's a very general form to unify the common distributions in this way. By unification, the B can take specific forms, AI can take specific forms. And so that can make other distributions, that the common distributions all fit to this form. So essentially, there are three functions, B, AI, and C. And they're all known functions for a specific distribution, like Gaussian distribution, Poisson distribution. You can specifically write out the corresponding forms of AI, B, and C. But we're just writing it in general in this case. Okay, any questions? And all right, so maybe we'll see more about this thing. Maybe I can give you one example about Gaussian distribution to see the connection. So in the Gaussian distribution, let's see, to make this as one example. Okay, so if we are having yi as Gaussian mu I sigma square. Then what's the density? The density yi would just be, I just put everything inside exponential function to have the same form. So I'm putting the constants outside of exponential, inside exponential. So I will have yi mu I minus 1/2 mu I squared sigma squared minus yi squared 2 sigma squared minus 1/2 log 2 pi sigma squared. So this is actually equal to the form we are familiar with. 1 over root 2 pi sigma exponential minus yi minus mu I squared 2 sigma squared. So it's exactly the same thing. I'm just trying to rewrite this into this form so I have a better correspondence with exponential family. So therefore, you see by matching the terms, we would have here mu I is just sigma I, right? And we would just have phi equals to sigma squared. So the location is the mean, scale is the variance, and correspondingly, our B function here, B function applied to theta I is just 1/2 theta I squared. So we see the form of the B function by matching them, and AI phi is just the identity function. It's just itself. And then this remaining term, this term here, is just the C function we need for the normalization. That's it. Okay, so basically we're showing that the normal distribution, Gaussian distribution, belongs to exponential family. All right, any questions? If no more questions, then we will talk about some properties about exponential family. Properties of this exponential family with two parameters, theta I and phi. What properties do we have? So if we have yi following, so let's say we have the yi, I just write it this way, yi follows this, then we directly have the closed form expression for the expectation in the variance of y. So the first property is about expectation. Expectation of yi is just the first derivative of the b function applied to theta I. We have this. And how do we prove this property? The proof can be done by using the fact that the density function integrates to 1. And then we take the derivative of the integral of the density function. Because the integral is 1, then the derivative is 0. Then we swap the differentiation and the integral. So we will have integral outside of differentiation. That's the trick we'll apply here. So let's see how we use it. So first, we start from the fact that integral fyi theta I phi dyi, this is equal to 1 by the definition of the density function. Then if we do the differentiation against theta I, d theta I phi, this is 0, right? The differentiation of one constant is 0. Then, in calculus, we need some conditions to swap the two things. But here we could do it because the density function f is a very smooth function. It's a smooth function. So we could swap the two. And then we would have integral outside d theta I fyi theta I phi dyi. So one thing I forgot to say here is that when we use the semicolon, we want to say, okay, before the semicolon, it is the random variable whose density we're writing out. And after the semicolon is the parameters involved in the density function. So we try to separate the random variable value and the parameters. So once we get to this step, then we just take the derivative against theta I using the form here. And specifically, the exponential function has a very special property of its derivative, right? We will get the derivative of its content, get it out, and then the exponential function will stay. That's the property we will use. So this will be the left-hand side will be, when we take the derivative against theta I, the second term doesn't involve theta I, so it's gone, only the first term. And we actually get yi minus b prime theta I, ai phi. That's the derivative of the exponent times the exponent, the exponential function will stay. So that's still fyi theta I phi dyi. And this is 0. And now we can separate the two terms. So basically, we can remove this denominator because it has nothing to do with the integration and it's 0 on the right-hand side. So we can remove the denominator. And then we can have one term involving yi, another term just b prime theta I. So essentially, we will just have yi times fyi theta I phi dyi equals to integral b prime theta I fyi theta I phi dyi. So we have this equality. And then we get what you want. So the left-hand side is basically the definition of expectation of yi. Right? It's yi value times the density value, then integration. The right-hand side, we can move b prime theta I out of integral, and the integral of the density is just 1. So the right-hand side is b prime theta I. And that's exactly what we want for the property. So this is nice because it gives us that expectation of the random variable that follows exponential family only depends on the location parameter, not the scale parameter. Okay, how about the variance? That's our second property. Second property is that the variance of yi is just the second derivative of b at theta I times ai phi. So now the scale parameter will kick in, and that makes sense as well, right? The scale parameter affects the how spread out random variable yi's distribution is. So it should for sure enter the variance. Okay. And for this one, the proof is very similar to this one. The only thing is that we will move on to the second derivative, not just the first derivative. So basically, to prove this result, we'll go to the second derivative as d squared d theta I squared of this integral. dyi. This is 0. And again, we've swapped the derivative with the integration. Okay, so basically we will have integration out, second derivative inside, d theta I squared, fyi theta I phi dyi. Okay, this is 0. Now, what's the second derivative? So we just go to the first derivative here and do the differentiation against theta I again. So, like both the terms, it's a product of this term multiplied by this term. Both terms involve theta I. So that's why we need to use that product rule for differentiation. But anyway, I'll leave this for to do it. We can show that after some algebra, the variance of yi is actually equal to this form. Yeah. So it's actually in the previous year's notes, and you can try this yourself. Okay, so that's the nice property about the mean and the variance. So now one thing we want to say is that recall in GLM, we define mu I, the mean parameter, as the expectation of yi. Now, if yi follows exponential family, then this mu I would be equal to b prime theta I, right? And also recall that we need the link function g mu I to be what? To be x transpose beta. We also need this. So for these two purposes, how do we define the link function? So one way I forgot to say is that theta I has, actually, there's one way to say theta I, which is, we can call it the canonical parameter. So there's a jargon out there, the canonical parameter. And for the canonical parameter theta I, what if we just directly, because mu I has some relationship with theta I, and we want the mu I to be we want the g of mu I to be a linear predictor. And recall that we call this theta I. We just introduced this eta I as a linear predictor. Eta I is g of mu I. So we have three things. Don't confuse yourself. Theta I, location parameter of exponential family. Mu I, expectation of yi. Eta I, g of mu I as a linear predictor. So there will be a natural thought. Can we reduce the three parameters to two parameters? So it's no longer this complex. For this purpose, the idea is to set eta I to theta I. So by doing that, you essentially have linear predictor set to the canonical parameter, the location parameter of exponential family. So linear predictor becomes the location parameter. You set it. Why is this reasonable? The reason is that in the exponential family, actually, theta I takes real values. So theta I is not a parameter that is restricted in the range. So this satisfies our desired property as the linear predictor, for the linear predictor, which should be real value. It should be no restriction. And that matches the theta I. And also, like I said, this way we can reduce three parameters related to the mean, eta I, mu I, theta I, to two parameters by setting eta I to theta I. And then you see what happens here is you would have mu I equals to b prime eta I. And b is the function, known function in the exponential family definition. So for a specific distribution like Poisson, you have the b known. And for Gaussian, we have the b here as this 1/2 square function. So for each specific distribution, you know the form of your b, and therefore the form of your b prime. So with this, you can directly say, I can just find the inverse of b prime so that eta I is just the b prime inverse mu I. And I define this to be my g mu I. Okay, so in this case, the link function is defined as the inverse of the b prime. And this is called canonical link function. So it just provides a way to specify the link function for a specific distribution. As long as you can write the distribution as an exponential family, find the B function, take the derivative of B function, then take the inverse of B function. That's your link function. Yes.
By assigning theta into with theta, are we not imposing additional restrictions that aren't there in the problem?
Are we imposing any restrictions on what?
On the structure of mu I, theta, and theta.
The restriction is, this is your link function. That's it. You're basically specifying your link function in this way, but there's no restriction on the range because, as I said, the theta I as the location parameter for exponential family, it takes real values. So its range matches the desired range for eta I. They're both real values.
Why can't theta is with some other theta?
So eta I is this, right? I say eta I is the linear predictor. That's the assumption. So what's your question?
Like right now you said theta equal to theta.
Yes, this is what we said, right? We set eta I to theta I. That gives us one way to specify the link function. But it's not the only way. It's not the only way. But this way has the justification that we can go back to the exponential family. Then we have an automatic definition of link function. It just simplifies the problem. Yeah.
Can you just remind me what theta and theta are before we set them equal to each other?
Theta I is the location parameter in exponential family. So whenever you write out a distribution in the form of exponential family, you will have theta I expressed in a way related to the mean of yi. Yeah, and eta I is what we assume, what we need in the generalized linear model. So it's what we call the linear predictor. It is what we assume for the ith observation. There is a parameter that is just the linear function of the predictors. So eta I is just a short notation for xi transpose beta. And since we assume g mu I, so mu I is the mean of yi. Maybe I just add here. Yi is mu I. So it's just that we transform the mean in some form in a monotone way so that it can be specified as a linear function. And we call this eta I. So yeah, so basically we have everything here. Eta I is g mu I is xi transpose beta. Mu I is b prime theta I. This is the property of exponential family. So we have three parameters related to the mean. Mu I, which is the mean. Theta I is the location parameter of the exponential family that's closely related to the mean. That determines the mean, I should say. And the eta I is the transform mean. That's a linear predictor. Yeah, so previously our question is how do we specify G, right? G is something we have to specify ourselves for the generalized linear model. But we are saying that if you set eta I to theta I, then G is fixed. Then you know what G is. Okay, but it is an assumption, but I should say everything here is an assumption, right? Why would you specify linear way, right? And then why would you specify yi to follow certain distribution? A Gaussian distribution, Poisson distribution, they are all assumptions. But we're trying to say that these assumptions allow us to separate noise from signal. I think that's the fundamental task of statistics or statistical modeling. So in this random structure, systematic structure separation, we are regarding the random structure as the noise, as the thing we don't care about, but we want to account for. The systematic structure is the signal we want to capture. So that's why our beta is our parameter of interest. Yeah.
So if you set beta to theta,
yeah,
your link function is the inverse
Inverse of
the
derivative of B. Yes. Yeah, that's right. That's exactly right. Then let's see what we can use the canonical link function. Yeah, maybe we will do that next. Let me see. Yeah, maybe we can do it next time as an example. Yeah, for today, we'll stay here, and then we will continue to say about parameter estimation for beta in this general exponential family form. So later, we would be able to say, oh, maybe I'll give example right now. Yeah, I think it's better to give example right now, so then you will see what we mean. So basically, let me see. Right, I'm still debating whether I should, maybe, okay, I'll come back to my original thought. Okay, so we will do the example for logistic regression, Poisson regression together and show why the link function we use in common logistic regression and Poisson regression is the canonical link function. So we'll do the verification for specific cases later. Okay, but for now, the question is, how do we optimize the parameters, right? So what is the parameter estimation thing? All right, so again, we will do the likelihood. So you see, the good thing about assuming exponential family is that log likelihood takes a very nice form. It's because once you take the likelihood, you are multiplying the density functions of y1 to yn, since they are assumed to be independent. So you multiply their density functions to get likelihood. Then once you multiply outside of exponential, it becomes a summation inside exponential. And once you take the log, exponential is gone. So it's actually very easy to work with log likelihood. So basically, we can see that, okay, the question we want to answer is how to estimate beta, right? Don't forget, we are interested in beta. That's the parameter of our ultimate interest, not mu I, not eta I, not theta I, but beta. So we need to write down the likelihood. So likelihood of beta, we define it in the way as the product I from 1 to m, fyi. But don't forget that we don't have beta written out here yet. We just have theta I and we have phi. But finally, we want to just express it in terms of beta. So maybe I'll just say put beta here. And also don't forget that we have the phi, which cannot be expressed for beta because beta is only linked to the mu I, eta I, theta I, but not the phi. So maybe I'll put phi here as well. So beta and phi. Phi is just like the sigma square. We also need to estimate for linear model. So it cannot be handled by beta. All right. Then for this density function, probably now for now, let's try to see how we can transform theta I to beta. What's the relationship now? So by setting theta I to eta I, you actually have theta I being eta I is actually xi transpose beta. So these two things are now linked together. So therefore, when I write down the density product, I put exponential distribution here. And inside, I change theta I to xi transpose beta. Yi xi transpose beta minus b xi transpose beta. Ai phi, this stays. And the second term has nothing to do with beta, it stays. That's it, okay? So then you see, I just need to move this product inside expectation to become a sum over I, right? And then I take the log. So the log likelihood I call it small l beta phi. The log likelihood would just be summation I from 1 to n. Inside the summation, I have two terms. yi xi transpose beta minus b function at xi transpose beta ai phi plus c yi phi. That's it. This is my log likelihood. And the goal is now to find a maximizer of the beta, of this in terms of beta. So how do we find max beta for this, right? So essentially, you see the second term can go away because it doesn't involve beta. It's just the first term that matters. How do we find the beta value to maximize this term? Okay, and this becomes an optimization problem. It really depends on whether there's a closed form or not, depends on the B function. What the form of the B function takes, it will determine the difficulty for the optimization problem. And recall that for the normal distribution case, the B function, when the B function is just 1/2 xi transpose beta squared. That's the case for the normal distribution. And because this is a vector form, right? So basically xi transpose beta give me a scalar, but I can open it up as a vector form. So then you see that I would have a square form for beta here. I'll just say it. So it's basically beta transpose xi transpose beta. So I can open it up in this way. And this one is a square term for beta, and this is just one beta. So in this case, for this B, the optimization is easy. I just take derivative against beta, and I'm done. That's exactly what we get for the linear model case, right? So we have that. But for more general B, for other distribution where B is not so nice, then we will have a problem. So that's why when it comes to generalized linear model, the optimization becomes a bigger challenge than linear model. And you can imagine the generalized linear model was probably developed, I think if my memory is correct, it's in the 1970s, when generalized linear model was developed as a statistical methodology. But at that time, computer was still not there yet. So how do we do calculation easily, right? It's not too intensive. So this is where we will talk next about the optimization, which actually turns out to be a very nice idea, I would say. And this idea is still used nowadays. That is, we turn this optimization problem into iterative application of the least square. Then as long as we can solve least square, we can solve this problem. We just need more iterations. And that makes the computation feasible when we don't have so much computational power. Okay, so now the next topic is focusing on this optimization. To talk about optimization, we will just quickly review a basic second order optimization method called Newton-Raphson method. So we'll start from there. And then we'll see how it is modified for the generalized linear model parameter estimation problem. I want to add a note that nowadays, because statistical methods, I'll just finish this, because statistical methods are getting more and more complex. So a lot of the parameter estimation problem becomes optimization problems. So that's why optimization, which is not traditionally a topic taught in statistics, has become more popular nowadays. And students here may go to the EE department to take an optimization class. So.
Well, so, sorry, can you say once more what your point was about when the B function is just 1/2?
That's the.
What's the takeaway there?
The takeaway is that the optimization is just trivial. You just take the derivative against beta, set it to 0, and solve for beta. Yeah, that's the least square solution. Yeah, but I'm saying that when the B is not in this form, in some other forms, the optimization is not trivial. Yeah. Okay, so then let's review some optimization method. I mean, in terms of what we need here, the Newton-Raphson method. So here, we will have a function to optimize. And the function is called f. The f function takes p-dimensional vector and outputs a scalar. So it's a real value function. And our goal is to optimize the function. So our goal is to find beta, we call it beta star, such that f at beta star is bigger than f at any other beta values. So this is called the global maximum. So we want to find the global maximum of f. That's the question we want to answer. Okay, and then the method we will talk about is called the Newton-Raphson method. It's called the second order method because you will need a second derivative. So we call that NR method in short. So it will use two concepts for such a function that's real value but takes vector as its input. So the first one is called gradient. Gradient is the first derivative of f. And it's called this. This is called, how to say it? It's the reverse triangle of f. And this gradient will be a p-dimensional vector. So basically, we'll map RP to RP. And what's the definition of it? So basically, the gradient of f at a vector value beta is just defined as a vector of partial derivatives. So it's partial f partial beta 1. It's the first dimension of beta at beta. 2 partial f partial beta p at beta. So it's a p-dimensional column vector. That's the gradient. So what's the intuition of this gradient is that it's about how fast my f value changes at the current beta value in every dimension. So this is the change in dimension 1. This is the change in dimension p. So I'm looking at p dimensions, so I have a vector. That's the gradient. And this is analogous to the first derivative. For the second derivative, it's called a Hessian. It's a P by P matrix. So here we just call it H sub F. It's a matrix and it's from RP to RP by P. It's a matrix. And its definition is based on second order partial derivatives. So in particular, you have P rows and P column. In the first row, we will have the first entry as partial square f partial beta 1 square at beta. And then the second entry will be partial square f partial beta 1 partial beta 2 at beta. And finally, it will be partial square f partial beta 1 partial beta p at beta. That's my first row. And my last row would be partial square f partial beta p partial beta 1 at beta. And second is partial square f partial beta p partial beta 2 at beta. Finally, partial square f partial beta p square at beta. So it is often a symmetric matrix because basically which one you take partial derivative first will not change the result. When that is the case, then you have a symmetric Hessian matrix. So like beta square f partial beta 1 partial beta 2 is equal to partial square f partial beta 2 partial beta 1. Then you have symmetry in this Hessian matrix. So the Hessian matrix, if we use the analogy in one-dimensional second derivative, the second derivative actually is about the curvature, right? The first derivative is about the slope. Second derivative is the curvature, how convex or how concave the curve is at that place. but this is the multi-dimensional p-dimensional version. Okay, so the Newton-Raphson idea is based on the fact that we want to have Newton-Raphson idea is that we hope at the maximum we're looking for this partial f at beta star. So beta star is the maximizer we're looking for. We want this partial f, we want the gradient f at beta star being 0. That's what we want. But why cannot we just directly do it? The reason is if you take the derivative, the gradient of f, set it to 0, you may not be able to solve it. So like this equation is not easy to solve. That's the challenge here. So then how do we approximate it? Idea is Taylor expansion, which is a very nice thing to turn the problem into a polynomial problem. So Taylor expansion, okay, this is the goal, but difficult to solve. Okay, then we use Taylor expansion to help us. Basically, we want to use Taylor expansion to simplify the gradient function. So the solution is use Taylor expansion to simplify this gradient f. That's what we want. So then we actually have this gradient f at beta. Approximately, we expand it at one value, beta 0. And typically, beta 0 is the current beta value we're looking at. And we're looking to move beta 0 to a next value so that the f function is bigger. So we want to try to find a better value for beta. So you can say that beta 0 is our current value, but we're going to update it. So when we expand that beta 0, it's actually Hessian f at beta 0 times beta minus beta 0. This is just a multivariate version of Taylor expansion. So we're expressing gradient f at beta by simplifying it in this approximate way. So beta 0 is the current value we are looking at. And we're hoping to find a better value. And with this approximation, because we said this real form, this actual form of this partial of this gradient f is difficult to solve. So how about we use this approximate form? So then we want to say that then at this ideal beta star, we know that gradient f at beta star is 0. So with this, then using this approximation, we just replace beta by beta star. So then what do we have? Then we will have this gradient f at beta 0 plus Hessian at beta 0 times beta star minus beta 0. This is approximately 0. Okay, and then this gives a way to solve for, if you set this to be 0, pretending the approximation is good, then you have a way to solve for beta star, which is so much easier to solve than this one, right? Because then this will give you beta star is approximately what? Is approximately basically beta 0 minus the Hessian at beta 0. I take the inverse of this times the gradient f at beta 0. That's it. I'm just doing the algebra for this term. Expand it and then move the beta 0 to the other side and this to the other side. And then that's it. So this is the update. This is exactly the update rule in the Newton-Raphson algorithm. So in each iteration at the current value, so let me just write this one more line before we finish. During the iteration, let's say that we want to go from the current value beta k to the next value beta k plus 1, right? In the kth iteration. Then you just use this formula. So beta k plus 1 is set to beta k minus the Hessian at beta k, inverse of the Hessian times the gradient of f at beta k. This is the update rule in Newton-Raphson. Okay, and this is called a second order optimization because we need a Hessian, which is second derivative. But how can we apply this to our optimization problem? Maximize the log likelihood. As I said in the old days, right? Without so much computing power, we hope to simplify the problem as much as possible. So Fisher, who was one of the very early day pioneer, maybe arguably the most important contributor of statistics, he actually proposed this idea of replacing the Hessian. Here, recall that our F matrix is the log likelihood. And log likelihood involves our observations y1 to yn, right? So he actually argues that we could replace this Hessian by the expectation of Hessian with respect to y1 to yn. So you're no longer involving y1 to yn from your data, but use the expectation from the distribution. And then you can simplify the form. So essentially, we're not using exact Newton-Raphson, but we are replacing Hessian by expectation. And that's what we will continue next time. And this approach is called the Fisher scoring method. So then we can simplify the form. And then we will further show that it can be reduced to iterated rate-weighted least square. So that's the algorithm used to solve GLM. And it's still used nowadays. Okay, so that's all for today's lecture. And we will continue with the Fisher scoring next time. And so I'll stay here for a while in case you have any questions.